Interval estimation, otherwise known as confidence intervals. So now we get into the part of the semester where we're using the information from our sample to say something or infer something about the population. So our first form of inference about the population is through confidence intervals. So we have a statistic collected on a sample, say the sample mean X bar. We also know that if we were to get another sample and calculate the sample mean on that sample, we would come up with a different sample mean. That's due to sampling variability. And we know how to describe the sampling distribution of this statistic. We know how X bar is going to vary from sample to sample. We had our 3 facts about it. It's shaped like a normal distribution as long as our sample size is big enough, or if our X's were collected from a normal distribution. The mean is mu, and the standard deviation is sigma divided by the square root of n, which we can use S over the square root of n to substitute if we don't know sigma. So let's put this information together to get an estimate of the population parameter and buffer this best guess based on the variability of the statistic. So we're going to use the statistic as our best guess at the population parameter, and we know it's going to be off by a little bit in general, so we're going to buffer this best guess with a range of values. So we can put all this together and estimate the population parameter with a range of values with a certain level of confidence, and this is going to be called our 1 minus alpha % confidence interval. All right, so a 1 minus alpha % confidence interval for mu when sigma is known is the following. It's X bar plus or minus our Z critical point times sigma over the square root of n. But we're not going to use that formula because that's not the one used in practice very much. We're going to be working with this one most of the time in this class, and that's the sample mean plus or minus the margin of error, but this time, since we're using S instead of sigma, the sample standard deviation instead of the population standard deviation, we're under the t distribution, so we have a t critical point in our margin of error calculation there. And the 1 minus alpha % lies between those two critical values, plus or minus your z or t critical points. But we're not going to worry about hand computations. You probably hand computed a couple times in your previous stats classes, but again, we're using R. We're going to focus on the applied, and we're going to use R like people would do in practice. Of course, we can calculate it by hand, but we're going to use R. Your textbook shows the calculations for these confidence intervals using R like a calculator. You can ignore all of those instructions and follow our guide in these lecture notes and also in the R help guide in Canvas and our lecture examples. So also note that we will only be computing intervals for the mean assuming the standard deviation is unknown. That is, we're using S instead of sigma, and we'll use the t distribution. All right, so these procedures require 2 assumptions: that the observations are independent and that the sample mean has a normal distribution. Now you can get the independence of observations either by having a random sample or ruling out dependence among the observations in other ways. The second assumption, that the sample mean has a normal distribution, you get either by having X come from a normal distribution or by the CLT. As the sample size grows larger, the distribution of the sample mean becomes closer and closer to a normal distribution. All right, so R is going to compute our t-based confidence interval using the t.test function. Now the t.test function is going to give us output for a hypothesis test and a confidence interval all at once. We'll just be paying attention to the confidence interval output for now. So we're going to work with the data set that's linked with your lecture notes in Canvas called directmail.csv, and it contains 3 columns: an envelope type, either logo or standard envelope, an offer of miles, either regular or no offer, double miles or use anywhere double miles for an airline, and amount charged on the credit card during the offer period. So this is a credit card company trying out different types of envelopes and different miles, sky miles offered. And they're measuring the amount charged during the offer period. We're going to find and interpret a 95% confidence interval for the mean amount charged over the offer period. Okay, so if you download directmail.csv, name it as an object in R, and then attach your data set, you'll notice that the 3rd column is called amount. And that's the one that we want to do our t-test, our confidence interval on, So we're going to use t-test with the amount column as our data set. And it does a one sample t-test for us. It tells us what our data was, that it was done on the amount column. It gives us a t-statistic degrees of freedom, which is n-1. 30,000 minus 1 is 29,999. And a teeny tiny p-value. We'll talk about that later, our alternative hypothesis. But we're going to focus on this little bit of output for now, the confidence interval that gets output. So notice that the default is a 95% confidence level. So it gives us the 95% confidence interval of 1775.46 to 1803.478. Now this last little piece of output is your sample estimates, mean of x. This is the sample mean. So that's exactly at the center of these two values for our confidence interval. All right, so we've got our confidence interval, and now we need to learn to interpret it. So we're always going to start by stating our confidence level. So we are 95% confident that what? What's our parameter? Our parameter is the population mean. So 1775.46, and this is amount spent, so it's in dollars, less than mu, less than 1803.48. So we're 95% confident the mean amount charged during an offer period like this one so that's our parameter. It's the population mean amount charged during an offer period like this one. Make sure you don't talk about the sample mean. That's what we use to get our confidence interval. We're making our inference about the population mean. So we're 95% confident the mean amount charged during an offer period like this one is between $1,775.46 and $1,803.48. And that is a confidence interval. Now I know you learned this previously, but it's just kind of a quick review, making sure that we're all on the same page. All right, so now if we want to find a 90% interval for the mean amount, how do we do that? Because R gives us, by default, a 95% confidence level. Well, I can use the t.test function again, give it the data set, which is my amount column, and then put another argument in my function. I'm going to put a comma in and then use the conf.level argument equals 0.9. And you'll notice when I do this, it gives me the 90% confidence interval. Now, how does a 90% confidence interval compare to a 95% confidence interval? Well, the bigger the confidence level, the wider the range of values. So a 90% interval is going to be more narrow than the 95% confidence interval. It doesn't span as far as the values for the 95% confidence interval. Okay, so we can plan ahead and get a sample size estimate when we're trying to estimate mu. So suppose we want to control the margin of error, otherwise known as the MOE. We can choose a sample size based on this constraint. So if we've got that the MOE has to be less than a certain amount, less than or equal, we can set it up this inequality where we define what the MOE is. The margin of error is, sigma is known as a z critical point times sigma divided by the square root of n, and we can just solve for n. So what I've done here is I've squared both sides to get rid of the square root on the n. And after manipulating with algebra, I get that n has to be bigger than or equal to z squared times sigma squared divided by the margin of error squared. And so now I've got a formula for calculating the sample size that I need in order to keep my margin of error within a certain bounds. What do we want? We want a narrow confidence interval because we want to be able to pinpoint that parameter. All right, so note that the z critical point for 95% confidence is 1.96. So let's do an example. Lenders often use FICO scores to determine the creditworthiness of an applicant. FICO scores range from 300 to 850 with a higher number meaning better credit, less risk for the company. Assume the standard deviation for FICO scores is 60. A lender would like to estimate the average credit score of a town in the Midwest. What is the required sample size if the lender does not want the MOE to be more than 20 at 95% confidence? Well, I can use my formula. I have my formula from the previous slide. N is bigger than or equal to the z critical point squared times sigma squared divided by the margin of error squared. I plug in my values. My z critical point for 95% confidence is 1.96. My assumed standard deviation is 60, so I plug that in, and the MOE I want to keep it within is 20. And when I calculate that with a calculator, I get 34.57. Now, can you get 34.57 people in your sample? I hope not. We need to have a whole number here. So to keep the inequality correct, we needed n to be bigger than or equal to this amount. So we're going to round up and take n equals 35 residents. Even if that decimal is 34.01, to keep that inequality true, we're going to always round up sample size estimates. So always round up sample size calculations to the next whole number. A similar calculation can be done for other confidence intervals, such as ones for P, the population proportion. And if you're doing one for P, the population proportion, and a best guess for P is not available, you're going to use P equals a half. All right, so we can talk about the sampling distribution of the sample proportion. We could have brought this up in the last set of lecture notes. I'll tell you why we didn't in just a minute. But a lot of textbooks and introductory stats courses use that the sampling distribution of p-hat is approximately normal, think the CLT. The mean of the distribution is the thing you're trying to estimate, p, and the standard deviation of the distribution is p times 1 minus p over n square rooted. And this is the distribution that's taught in your text and many others. But we're going to use the prop.test function in R to compute our confidence intervals for the population proportion P. And it uses something different than what that other confidence interval is, which is called the walled interval. It computes something different and is better than the walled, so we're going to use what is built into R. So let's do an example. We have 42 out of the 118 respondents to our beginning of semester survey responding that they think it's okay to use a cell phone during a college class. Find a 95% confidence interval for the proportion that agree. So we're going to use the prop.test function, and what it takes, this is covered in the R help page too, is your Y, your number of successes, your N, your sample size, and we're always going to put correct equals false in this semester when we use the prop.test function. That does it without continuity correction. Continuity correction is because the proportion, since it's y over n, is actually a binomial distribution, which is discrete. Think about it, that y is your number of successes out of n trials. But we're overlaying a normal distribution on top of that binomial distribution. And so some methods try to account for cutting off the corners of your histogram bars when you overlay that smooth curve with this thing called continuity correction. We're just not going to use that this semester. All right, so this is what the output looks like. And notice that it gives you hypothesis test output, and it also gives you a confidence interval, just like the t-test function did in R. So we've got our 95% confidence interval, and now we need to go ahead and interpret it. So let's remind ourselves what the prompt said. It was the proportion of students who think it's okay to use a cell phone during a college class. All right, so we're going to start with our confidence level. We are 95% confident. Make sure you use the word confidence because that is a statistical term and there are no synonyms for it in statistics. That the proportion of students who feel it is okay to use a cell phone during a college class is between 0.275 and 0.446. Now I could have turned this into percents and just changed it to we are 95% confident that the percent of students who feel it's okay to use a cell phone during a college class is between 27.5 and 44.6. And I can even reorder the words as long as all my ingredients are there. We're 95% confident that between 27.5 and 44.6% of students feel it's okay to use a cell phone during a college class. So as long as you have the right ingredients, you can reorder it however you would like.